Okay, in this video we're going to look at how we can compute arc length for a path described by a vector function, and then we're going to apply our result to problem number 2 on the worksheet. Alright, so let's say we have this blue path described by the vector function r of t, which in component form is given as x of t, comma y of t, comma z of t. And let's say we want to find the length of the arc along this path as we move from this point where t is equal to a to this point where t is equal to b. Okay, now complication, of course, is that at least in general, this path can be curved. Okay, so the idea here is to break up this arc into a bunch of little sub-arcs, and as long as our blue path is nice and smooth, meaning there are no sharp cusps or holes or breaks in our curve, then each one of these little sub-arcs will be at least approximately a straight line path. Okay, so the idea here is to measure the distance covered by each one of these little baby steps as we move from tick mark to tick mark. And then to get the total length of this arc, we're just going to sum up all of those distances. Okay, so let's do that. I've zoomed in on one of these little sub-arcs. Okay, now S is the letter that's typically used for arc length, so ds just indicates a little differential change in arc length as we move from tick mark to tick mark. So this is our baby step. Okay, and now as we move from this tick mark to this tick mark, we have to move a certain amount in the x direction, so that's this differential change dx, and then likewise we have to move a certain amount in the y and the z direction, so those are the differential changes dy and dz respectively. Okay, and now knowing what we know about measuring distance in R3, right? So ds here is at least approximately the distance from this tick mark to this tick mark. Okay, so ds squared, right, by two applications of the Pythagorean theorem, as we've seen earlier, this is just the sum of the squares of each one of these little differential changes. Okay, so put another way, ds is the square root of the sum of the squares of these little differential changes. And now since our vector function is in terms of the parameter, I'm going to now write this expression in terms of the parameter. Okay, so I can do that by multiplying by dt over dt. So in other words, I'm just multiplying by 1, which is not changing the value of this expression. Okay, now notice here, if I take this dt in the denominator and bring it into the root, it's going to come in as a square. And if I distribute it to each of the square terms in the root, okay, this gives me the square root of the sum of the squares of these derivatives, and then this dt from our numerator up here just stays outside the square root. Okay, so now this leads us to the following result. To find the total length of this arc, okay, I want to sum up all of these differential changes in arc length. Okay, the way you sum up on the differential level is you integrate. So I'm integrating ds as we let t vary from a to b, and from this result, this is equal to the integral of the square root of the sum of the squares of these derivatives, and we're integrating with respect to t, and we're letting t vary from a to b. Okay, now, before we jump into problem number 2, an easier way to remember this, and it also just offers a little more insight into what exactly this result is saying, is to note the following, right? So we're calling the components of our position vector r of t x of t, comma y of t, comma z of t. Now if you look at the velocity vector, that's where you just differentiate component-wise. The components of the velocity vector are dx dt, dy dt, and dz dt. So if I take the magnitude of the velocity vector, so in other words, if I look at the speed of our particle that's moving along our path, okay, that's the square root of the sum of the squares of these derivatives. Okay, so put another way, what we're really saying is that the length of this arc is really just the distance traveled by a particle moving from this point where t is equal to a to this point where t is equal to b. And to find that total distance, well, I'm going to take the speed of the particle and I'm going to multiply it by a little infinitesimal change in time. So speed times time, that's going to give you a little infinitesimal change in distance. That's your ds. And then we're summing those up as we let time vary from A to B. That's going to give us the total distance traveled by a particle moving along this path from this point to this point, okay? So I think this is nice because it's just, in many ways, it's a lot easier to remember than integrating this square root of the sum of the squares of the derivatives and all that, okay? So let's now illustrate this result with problem number 2 on the worksheet. Got to make some space here. So for problem number 2, okay, it says find the length of the curve, and it's described by the vector function r of t, whose components are natural log of t, comma t squared over 2, comma square root of 2t, and here t varies from 1 to e. Okay, so let's first compute the velocity vector, because ultimately I need to integrate the speed of our particle that's moving along this path, right? So v of t, just differentiating component-wise, that's 1 over t, comma, square root of 2. So then the speed, well, just take the magnitude of the velocity, that's the root of 1 over t squared plus 2. Okay, so now this is the thing I'm going to integrate. Now the one thing you want to keep in mind when doing problems like this is that these problems are designed so you are able to actually compute the resulting integral that you'll need to compute. Okay, so when I look at something like this, integrating this expression doesn't seem particularly easy. However, if we rewrite it doing a little algebra, we'll find that actually the integral is not that bad. Okay, so here's one way to do that. Okay, this is not exactly obvious, but this expression under the root is in fact a perfect square. It's 1 over t plus t quantity squared. So if you multiply this back out, you'd get 1 over t squared. Now for the middle term, you're going to get 1 over t times t, that's 1, and then you're going to get another 1, so there's that 2, and then you're going to get a t squared for that last term. So this is a perfect square. You're taking the square root of it, so 1 over t plus t, right, would be the simplified expression there. And notice here I don't have to worry about absolute value in removing the square root, and that's because t there is, in this case, is positive, right? It varies from 1 to e. So this expression 1 over t plus t is always positive. Okay, now a slightly different way to get there is to write this expression under the square root as just one fraction. And now when you look at 1 plus t to the 4th plus 2t squared, that looks a little more recognizable as a perfect square. It's 1 plus t squared quantity squared. Okay, and so now you can go ahead and remove square roots. And again, you don't have to worry about absolute value because t is always positive on this interval. And now split that up into two fractions and you arrive at that same expression. Okay, but however you get there, the nice thing now, right, is if I want to compute the arc length, okay, I want to integrate my speed with respect to time, and we're letting time vary from 1 to e. And as we just computed up here, our speed is 1 over t plus t. Okay, so integrate, we get the natural log of the absolute value of t plus t squared over 2, and then we want to evaluate at 1 and at e, and then we're going to take the difference, right? So evaluating at e, that's going to be 1 plus e squared over 2, right? Because the natural log of e is 1. If we evaluate at 1, we're going to get, well, just a half, because the natural log of 1 is 0. Take the difference there, and this simplifies to e squared plus 1 all over 2. All right, and that's going to do it. Thanks so much.